Newton's first law states that an object at rest will stay at rest, and an object moving at a constant speed in the same direction will remain moving at a constant speed in that direction unless stopped by an unbalanced force.
Have you ever wondered how a seatbelt keeps you safe or what its purpose is? The obvious answer would be that it keeps us safe. Of course, that is correct. The reason is much more complicated, and its purpose is in response to Newton's first law. When driving at a constant speed, the car and individual in the car are moving with the same velocity or share the same state of motion. When the speed of the vehicle changes abruptly, this does not seem to affect the passengers in the car in the same way. Upon contact with the obstacle, the car that was originally in motion has been brought to a halt by an unbalanced force. Unless the passengers of the vehicle are wearing their seatbelts, they do not decelerate to rest and instead continue their state of motion. The seatbelt's purpose is to allow the passengers to share the motion of the car. The above scenario would be difficult and dangerous to enact. Therefore, similar circumstances were recreated to mimic the continued motion of a passenger if a seatbelt were not worn. Predictions. Based on Newton's first law, also referred to as the law of inertia, the velocity of the objects placed on the longboard should remain the same or be equal to the velocity prior to the halt of the longboard. In other words, because there is no force acting on the stuffed animal or pill bottle, they should continue moving with an equal velocity. Both objects tested should continue to have the same horizontal velocity, therefore the initial horizontal velocity and the final horizontal velocity should be the same, as shown in the equation. Let's test it. To capture this phenomenon, a video capturing the forward motion of two items propelled by a longboard was created. The items used for this experiment were a longboard, a stuffed animal, a pill bottle, and a curb. The longboard was used to simulate the motion that can be seen in a vehicle, and the curb was used as a stop that simulated what happens when a vehicle comes to a complete stop. The stuffed animal and the pill bottle were used to simulate passengers in a vehicle, and each item was placed on top of the longboard and tested individually. This was done to capture the continuous forward motion of each of our passengers once the longboard came to a stop to demonstrate Newton's first law of inertia.
Our first example, we will be showing a stuffed animal on a longboard. So, as you can see in the photo shown, this is the object that was used for the previous example, and it had a weight of 2.4 ounces, also equivalent to 0.068 kilograms. So over here we are showing graph 1, where the velocity values for both the longboard, which is shown on the top line, and the stuffed animal, which is shown on the bottom line, can be seen. The longboard has a velocity of 2.99 meters per second, and the stuffed animal has a velocity of 3.05 meters per second, resulting in a percent discrepancy between the two velocities of 2%. The collision occurred around 1.5 seconds. The second graph shown here shows the stuffed animal still in motion once the longboard comes to a stop. The after values of the stuffed animal's velocity resulted in 0.99 meters per second. For our second example, we will be showing a video of a pill bottle on the longboard.
Go.
So as you can see here, this is a photo of the pill bottle used in the previous example, which had a weight of 4.4 ounces, also equivalent to 0.1247 kilograms. Now shown here is graph 1, which shows the movements for the pill bottle from start to finish, with a collision that was around 1.3 meters per second. The second graph shown shows the pill bottle movements after it left the board, with a velocity of 1.512 meters per second, and this visualizes the motion after. The third graph states the motion before the pill bottle's movement while on the board, with a velocity of 2.799 meters per second. The fourth graph shows the motion frame for the longboard until it came to a halt with a velocity of 2.907 meters per second, also resulting in a percent discrepancy of 3.5% between the velocity of the longboard and the pill bottle before the longboard came to a halt.
As shown in the table, the stuffed animal, which had a mass of 0.068 kilograms, had an initial velocity of 3.05 meters per second. The initial velocity of the longboard prior to its abrupt halt was 2.99 meters per second. The percent discrepancy between the two initial velocities was 2%. The final velocity of the stuffed animal was 0.99 meters per second. The object did continue its motion, however, other forces, such as friction, can explain the lower final velocity. The pill bottle, which had a mass of 0.1247 kilograms, had an initial velocity of 2.799 meters per second. The initial velocity of the longboard prior to the abrupt halt was 2.907 meters per second. The percent discrepancy between the two initial velocities was 3.5%. The final velocity of the pill bottle was 1.512 meters per second. The object did continue its motion, however, as mentioned before, other forces such as friction can explain the lower final velocity. What we have concluded following our experiment. We had originally predicted that the initial velocity of the items, stuffed animal and pill bottle, would be the same as the final velocity or the velocity after the longboard came to a halt. There were small discrepancies between the gathered data that can be explained by friction forces. In the case that friction becomes an acting force on the pill bottle or stuffed animal, it is possible that the continued motion of the objects will have a lower velocity than the initial. For both items, the final velocities, the velocities after the item's continued motion and the longboard came to a stop, were less than the initial velocities, the velocities of the items while on the longboard before it came to a stop.